Hello, good day. Welcome once again to our learning session. We are now on learning session 7 of our project construction and management, which is entitled Time Scaled Event Network. Okay, so this network is used to monitor the progress of the ongoing projects. Okay, so this is very essential for an engineer and the project manager for their monitoring of projects. Okay, so now let us start in our discussions. Let's go to our presentation. Okay, so the Gantt chart. Okay, so this is the chart used in time scaled event. Okay, so this is a very popular tool for planning and scheduling. Okay, so Gantt chart. I hope you are all familiar with Gantt chart. Okay, so in our course in engineering, this is very common. So I hope that you will study or research of the different kind of uses and types of Gantt chart used in this course or in this subject. Okay, so this is the aid of the project manager to schedule project activities. Okay, then this tool also is the one being used to monitor the progress over time by comparing the planned progress to the actual progress. So meaning, if you have this network or chart, it is easy for you to decide something if there are problems of your project. Okay, so okay, let's continue. Okay, so for example, this project schedule or this CPM diagram network. Okay, so I will show you the examples of this time scale network. Okay, so this one, if you can see, this is a project. Okay, so one project, then the activities are this one. Okay, so activity 1 to 2, 2 to 3, 3 to 5, sorry, 3 to 6, 6 to 9, this is dummy, 6 to 10, then 10 to 11. Okay, so this is the finish event. Okay, so the other part is 1 to 2, 2 to 5, 5 to 7, 5 to 7 to 10, then to 11. Then we have 1 to 2, 2 to 4, 4 to 5, 5 to 7, 7 to 10, then 10 to 11. Okay, so then we have activity 1 to 2, 2 to 4, 2 to 8, and 2 to 7. So those are the paths of this network. Okay, so let us see how this CPM diagram network being placed in a Gantt chart used as a time scale event. Okay. Okay, so this one, time scale activity diagram bar type based on early start. Okay, so this one, so these are the number of let us say weeks or days or the duration of the project. Okay, so that's 30. Let's assume that this is week 30 weeks. Okay, so then we have 1 to 2. So this is a 10. Okay, this is the number of days. So if you observe, this line is aligned with this bar. Okay, so this is the our reference for days. Okay, so activity 1 to 2, we have 2 to 4, 4 to 5, 5 to 7, then 7 to 10, then 10 to 11. Okay, so these are the dummy lines. Okay, so if you observe, this is the critical path. Okay, the longest path among the network. Okay, okay, so if you observe, if you are an engineer or a project a manager of a certain project, it is easy for you to tell the situation of your project or the status of your project. Okay, so if example, if this activity, you are on the eighth day, but your completion is somewhere here or 50%, so you are delayed. Okay, so you need to catch up to your schedule. Okay, so that's the good thing of this diagram. Okay, next, we have time scale activity diagram based on early start. Okay, so actually this is the same, but this is added. This one, the percent of project completion, the proposed and the finish. Okay, the percentage of each activity. Okay, then we have this one. So arrow. Okay, so time scale activity diagram bar type based on early start. So actually this is the same, but arrow is being used for the diagram. Okay, next, this one, uh, dotted line is being added for project monitoring purposes. Okay, okay, so okay, then this one, okay, so actually it's almost the same with the other ones, guys. Okay, then we have manpower labeling. Okay, so remember that in our project, one of the important resources that we need to use or utilize is the manpower. So imagine if you have a lot of manpower and you don't know how to use this one or to manage this one, you cannot meet your target even though you have many people but they are poorly managed or the allocation of manpower to a certain activity is not that good. Okay, so we need to analyze the skill of the people and how many manpower needed in each activity. Okay, so if you are a big contractor, so there are many projects, so you need to utilize your manpower so that it will benefit your company and minimize cost uh, to your end. Okay, so manpower labeling. Okay, so employment fluctuation and equipment adds to the cost of the project. Okay, then this is a problem where the only solution is to keep employment at an acceptable level. Then the use of activity flow to label resource requirement is illustrated in the following hypothetical project. Okay, so like this one, if you have this diagram, you can see the deployment of the personnel or the people among the activities. Okay, so this is the example. Example for this 1 to 2, you have this 15 men for 5 days. Then this one, 10 men. So every activity has assigned a number of personnel. Okay, so this is good if you have many projects. So you can utilize this. If example, if one activity you have civil works, your civil people finish this one, then you have another project. So you can use those people to your uh, other projects. Okay, so meaning many projects, one group of personnel, okay, with the same skill. Okay, so meaning you save cost and your company will benefit from it, but you have to properly manage those people. Okay, time scale system network with manpower loading, so they are being infused. Okay, or uh, bar chart, and the manpower loading. Okay. Then we have equipment constraint. Okay, so remember that in big projects, equipment are very usable. Okay, so the purpose of that one also is to expedite your project and make the work easier. Example, if you have excavations, big excavations for your foundations, so you need backhoe or other earth equipments to do the job. Okay. Okay, so but the problem if you have limited equipment also, many projects, so you have to use equipment utilization method for that one. So that is equipment constraint. Okay, so if the equipment requirements fluctuate, of course equipment will be idle for some time, and if rented for a short period, example, if there are problem with your equipment, the rental might be too high, okay, due to fixed expenses for moving in and out of the project. Okay, so meaning the mobilization of the equipments. Okay, so imagine if there are you have one equipment who will fail, so then you have no other choice but to rent. So the rented price is very high. Okay, so that is why we need to properly utilize and maintain also our equipment. So if you are assigned in or you are enjoying in a big company, construction company, maintenance of equipment is very important in their operations. Okay, so they include that one in their budget so that their equipment will be always doing good and properly maintained. Okay. Okay, now we are on the probable time estimate, okay, or PERT or PERT. Okay, so PERT is a management tool that is suited for research and development of projects which are generally repetitive in nature and is sometimes called once through projects. Okay. Pert handle the uncertainty problem by the use of three time estimates. Okay, so they are the optimistic time, then the most likely time or probabilistic time, then the pessimistic time. Okay, meaning you assume the days or your days you target a date which you have to meet the optimistic time, the most likely time, and the pessimistic time. Okay, so optimistic time, estimated minimum time an activity will take. Okay, so this is the activity duration when all the breaks are right. Its probability is about 1 in 100 or 1% represented by letter A. Okay. Then we have most likely or probabilistic time. It is defined as the estimated normal length of time an activity takes. This is the time expected that will most frequently be required for an activity if it were done again and again under identical conditions represented by letter M. Okay, so we have A, then M. Optimistic is denoted by A, then the most likely or probabilistic is denoted by M. Okay, so pessimistic time, this is defined as the estimated maximum time that will be required under the worst conditions. Okay, so its probability is about -1 in 100 or 1% represented by letter B. Okay, so pessimistic time is denoted by letter B. Okay, so let's review. Optimistic is denoted by A, probabilistic M, then pessimistic time is letter B. Okay, so this is the example of a curve. Okay, the probabilistic curve. Okay, so we have 0, the activity start, then optimistic time, then the probable time, M, estimated time, then the pessimistic time. Okay, so meaning this is the worst time or the delayed time of a certain project. Okay, then we have expected time. Expected time is computed by A plus 4M plus B divided by 6. Okay, so this is the expected time. Then the variance, the formula is B squared over 36, or it is equal to B minus A squared over 36. Okay, so please remember these two formula, expected time ET and variance. Okay, then the standard deviation of the expected time for each path is this one. So V path square root of E, or the expected time. Okay. Okay, so let's try one example. So I will prepare my writing materials for this one. Okay. Okay, so we have first to deactivate this camera so that we can activate this one. Okay. Okay, so I think this piece is okay. So okay, okay, okay. So let's try one example, guys. So example. Okay, so I hope you can see the sample. Okay. Okay, so we have this diagram. Okay, so it's visible. I hope it's visible. Okay. 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 Okay, so this diagram, okay, so this one, okay, so this is A, B, C, D, then we have E, F, F, then we have G, then H, then I. Okay, so I hope it's clear. So these are the activity A, B, C, D, E, F, G, H, I. Okay, so I hope it's okay. Then, so so the optimistic, probabilistic, and pessimistic time is given. Example for activity A, we have 2, 3, and 4. Okay, so meaning in our back in our discussions. Okay, so let's go to our discussion. Okay, so the first number is the optimistic, the estimated minimum time, then probabilistic estimated normal length, then the pessimistic is the maximum time. Okay, so those are the three. So let's go back. Okay, so this is optimistic. Okay, so optimistic, probabilistic, and pessimistic. Okay, so let's continue to the example. Then for activity B, we have 2, 4, and 6. Then for C is 1, 3, and 4. Okay, so I think my numbers are congested, but I hope you can follow. Then we have letter D, we have 3, 4, 5. 3, 4, and 5. Okay, so E is 3, 5, 7. 3, 5, and 7. Then F is 5, 7, 9. 5, 7, and 9. Okay. Then we have letter G. This is 2, 4, and 5. Then H is 4, 5, and 6. Okay. Then I is 3, 4, 3, 4, 6. Okay? So, example of this one, we have to compute for the expected time for each activity and the expected duration for each path. Okay? First, we have to write the solution. Okay, so solution. Okay, so we'll make a table for this one. Okay, we have path. Okay, so I hope path, then activity. Okay, so activity y. Okay, that is activity. Then we have the time, meaning that is the A, B, and aim and B. The optimistic, probabilistic, and pessimistic. Okay, we have now the estimated time, which is equal to 4. Sorry, so this is A plus 4M plus B over 6. Okay, so that's the formula. Then we have path total. Okay. So the path for this one, for this diagram, we have path A, B, C. Okay, so we'll write this one. This is path A, B, and C. Okay. Then the activity for this one are, okay, so A, B, C. A, B, and C. Okay, so we'll reduce the letters to see the space. Then we have path D, E, F. Okay, so D, E, and F. So the activities for this one is D, E, and F. Okay, so that's one. Then so for the last path, we have uh, G, H, I. G, H, and I. Okay, so the activity for this one is G, H, and I. Okay, so that one. Okay. So the times will just fill the numbers from this given to this one. Okay, so for A we have 2, 3, 4, 2, 3, 4. Then for B we have 2, 4, 6. And for C is 1, 3, and 4. Okay, so now we will compute the estimated time for this one. Okay, so for this one we have our A. So I will just point. Then you try to calculate. Okay, so we have A. So A is 2. Then M is 3. So 4 times 3 is 12. So plus 2. Uh, 12 plus 2 is 14 plus B is 4. So 18 divide 6. So 18 divide 6, that is 3. Okay, so meaning the estimated time for this one is 3. 3. Then for this one, 2, 4, 6, we have 2, 4 times 4 is 16. So 4 times 4 is 16, 2, 18. Then 18 plus 24 divide 6 is 4. Okay, so for this one, we need to calculate. Okay, so A is 1, 4 times M, 3, so 12, plus 1, so 13, plus 4 is 17, divide 6, we have, so if we'll calculate that one, the answer is 2.83. Okay, so the path total for this one, path total, so this is 9.83. Okay, so that is the path total. Okay, so for this one, so we'll just fill the numbers here. So 3, 4, and 5. Then we have 3, 5, 7. Then we have 5, 7, and 9. Okay, so if we fill this one, 3, 4, 16, 4 times 4 is 16, plus 3, 19, plus 5, so 24. So this is 4. 24 divided 6 is 4. Then we have 3. 4 times 5 is 20. 23 plus 7, so 30. Divide 6, so that is 5. So 4, 5, and this one is 5, 7, and 9. So 7 is M. So 4 times 7 is 28, plus 5, we have 33, plus 9 is 42, so we have 7. So 4, 5, and 7. So the total path for this one is 7, 16. Okay. Then we have for G it's I. So 2, 4, 5. 2, 4, 5. Then 4, 5, and 6. Then 3, 4, 6. Okay, so those are the numbers. Then the estimated time, so I will just write 3, this is 3.5, then 5, and 4.16. Okay, so the path total for this one is 12.66. Okay, so compute the expected time. So we already compute the expected time uh, per path and per activity. Okay, so this one, so activity A, the expected time is 3. Okay, so that one. Then for the critical path for this one is 16. So this is the critical path, which is the longest uh, path among of the project. Okay, so next we have to compute the variance for each activity and the variance for each path. Okay. So for variance, maybe I will explain. We'll just use the formula. So let's go back to the formula. Okay. Variance. So for variance, we can use this formula b minus a squared over 36. So meaning we just need to example for this activity 2, 3, 4. Okay, so the formula for variance is, okay, so let's go back to the cut. Okay, so the formula for variance is b squared. Okay, so maybe I hope you follow this one. Okay, so I will focus the camera. Okay, so this is the computing the estimated time and the critical path of this network. Okay, so next we will compute the variance. Okay, so I will just need to erase this one. Okay. So we need to compute now the variance of each activity and the variance of each path. Okay, so so DEF, so this DEF, then G, it's an I. Okay, so so the time, so we erase the time. So let's go back and write the time for this one. So we have for A is 234. Okay, now the formula for variance is B squared is equal to B minus A squared over 36. Okay, so we need to compute this one. Okay, so for this one we have B is 4 minus 2. 4 minus 2 is 2 squared. So 4 over 36. Okay, so this one is 4 over 36. 4 over. Okay, so we need to save the space. So 4 over 36. Okay, then for activity B to 4, 6. This one is B. So B is 6 minus A 6 4 4 squared is 16 over 36. 16 over 36. Then we have for this one D is 1 3 and 4. Okay, so 1 3 and 4. So B is 4 minus 1 3 9 over 36. 9 over 36. Okay, so this is now the variance in each activity. Okay, then for the path, the variance total is actually if you want decimal points, you will just divide these numbers. Okay, so the total uh, variance of this path is, so we'll add 20. So this is common denominator. So 29. 4, 16, and 9 is 29 over 36. Okay, so if we divide this one using our calculator, this will become 0.805. Okay, so meaning the variance of this path is 0.805. Okay, so if we continue this one here, okay, so let's check. Okay, so we just adjust this one because the space is very limited. So for D, we have 3, 4, 5. Okay, 3, 4, 5. Then for 3, the variance of this one is 5. Minus 3 is 2. So this is 4 over 36. 4 over 36. Sorry for the limited space. 4 over 36. Then we have 357. 357 is 7 minus 3 is 4. So this will become 16 over 36. 36, so that is 36. So 4 over 36, 16 over 36. And for F is 5, 7 and 9. So this is 9 minus 5, 4. So this is 16 over 36. Okay, so the total for this one is we have 36 over 36 or 0, sorry, so that's not 0. 1.0. Okay, so that is the variance of the critical path. Okay, the critical path, remember, guys, is path DEF. Okay, so this is the critical path. See the variance of the path, variance of the path. Okay, so is this one. Okay, so let's continue to end this example. So for G, we have 2, 4, and 5. So 2, 4, and 5. So 5 minus 2, we have 3. So this is 9 over 36. Okay, so for 4, 5, and 6, we have 6 minus 4 is 2. So this is 4 over 36. Okay, then we have 3, 4, and 6. 6 minus 6 minus 3 is so then 9. So 9 over 36. Okay, so we have 9, 9, and 4. So 18 and 20. So this is 22 over 36 or 0.611. Okay, so this is the variance of this path. Okay, so we already solved the expected time in its activity and path. We identified the critical path of the network, which is this one. Then we compute the variance in its activity and path. Okay, so I think okay, so that's the example. I hope you follow. So you follow that one. Okay, so V is the variance. Okay, so V is for or the variance. Okay, so that's the example of computing the PERT. Okay, so thank you. And this is all for this learning session. Thank you.